is 33.9 LC circuit. So the LC circuit obviously contains an inductor and a capacitor. So we have an inductor L and a capacitor C. So let's put it together. So we have a capacitor like that, and then we have it connected to an inductor. So the capacitor will have a certain charge Q on it, and the inductor has inductance L. So let's say, for example, let's put a switch here before we go on so that we can turn it on. So let me put a switch here. So let's say we have a charged capacitor this way. So capacitor is initially charged. So we can imagine that there's a battery connected to this setup of L and C, the capacitor and inductor at some point. So the capacitor is charged initially. And then we can say when the switch is closed, the capacitor discharges into the inductor, or capacitor discharges, and the current flows. So we call the current I flows through the circuit. So we can close this again now. And so now there's a current I flowing through the circuit once the switch is closed. So then the magnetic field is going to go this way, B. So we shall say then that the capacitor will now positively charge this way. So the capacitor is now fully charged. So capacitor is charged with opposite polarity, and then the cycle continues. Okay, so the capacitor will now recharge. So the current is the capacitor charges in the opposite direction with opposite polarity, and then it will now discharge in the opposite direction this way. So let me draw it for you. So yeah, so you have positive here, positive, negative, negative. So it now discharges this way. Okay, so what the effect you will be seeing then is just as a current which is sloshing back and forth. Okay, so it's charging one way and then discharging the other way. So it has the effect of a mass on the end of the spring. So we can say that this oscillation of the current in the LC circuit is like the oscillations of a mass on the end of a spring. Okay, so for example, you have a mass on the end of a spring like that. This mass is M, so it's just going to oscillate back and forth. Eventually, it will lose energy and come to a stop, and that will also happen in the LC circuit. The energy will eventually be lost in the spring, and the oscillations will stop. So what we are seeing then is just it's just an oscillation, or it's a sort of oscillatory circuit where when you charge the capacitor and close the switch, the capacitor discharges through an inductor and reverses polarity, and then discharges again the other way, and it just keeps going back and forth. So it's going to oscillate back and forth until it loses energy and stops, just like a mass on the end of a spring, which oscillates back and forth until it comes to a stop. Okay, so that's the oscillations that we are talking about in an LC circuit. We expect the energy stored in the LC circuit to be given by total energy is energy stored in the capacitor plus energy stored in the inductor, like that, where we know the energy stored in the capacitor is Q squared over 2C. Energy stored in the inductor is L I squared over 2. Okay, so we can use that. So total energy is therefore given by Q squared over 2C plus L I squared over 2, that way. And then we'll continue with that. So the rate at which energy is changing, the rate of energy change is du dt. So if we take the derivative du dt, then we shall say du dt is equal to d dt of Q squared over 2C plus L I squared over 2, like that. And so we can take this derivative and we'll see that the rate at which energy is used is equal to Q over C, and then we have the Q dt. The 2 goes away when you take the derivative, and then you're going to have L Our current is di dt, so we have L I di dt.
Is it d mu?
D mu du du dt. And we shall recall that the current is given by dq dt in the circuit. And so current is dq dt. So we can use that. So di dt. So we can say this is d squared q dt squared, like that. So I is d squared. So we can say q over c dq dt. So q over c dq dt, which is I, plus L, and then you have I dq dt, no, I d squared q, hold on a second, and that should be equal to substitution, du dt, equal to 0. So, yeah, let me put this here, hold on a second. So total energy is Q UC plus UL, so this du dt equals to 0 here. So this whole thing is equal to 0 because the total, assuming energy conservation, there is no change in energy, so Q equal to 0. So we can write Q over C plus L d squared Q dt squared equal to 0. The current I's cancel out. So you can write Q, actually let's do it this way, Q, so we have Q plus L over C. Suppose we can do, yeah, Q over C plus L d squared Q dt squared. So let's do this instead. Hold on a second, Q over L C plus d squared Q dt squared equals 0. So you can just rewrite it as d squared Q dt squared equals minus Q over LC. What was the question?
On that first line right there, you have QCI plus LI. Oh, right there where you were at.
Yes. Yeah, here.
How did they cancel?
Well, when you divide through by I, because there's 0 on the other side, it goes away. You can divide through by I on both sides, and that should take the I away. So you understand, you have 0 on the other side, so if you divide through by I, that's going to be gone. Or if you want, you can just leave it in there. So you say Q over CI equals minus LI d squared Q dt squared. In the same way, you can cancel your I's. Okay, so if you like, you can do it that way.
Is the d squared on top, is that the second derivative?
Second derivative, d squared Q dt squared, yes. So this is where we are, and so the question, or what we want to do is to compare this to an oscillation, a mechanical oscillation. So we can say this is similar. So we already said this is the same as the mechanical oscillation of a spring. So for mechanical oscillations of a mass m on a spring, you can just say that let's make omega squared be equal to L over 1 over LC. Okay, so if we make omega squared be equal to 1 over LC and Q be equal to X, then we can say that this is the same as writing d squared X dt squared equals minus omega squared X. Okay, so this is, we know the solution to this type of problem. So we can say we know the solution to this. So we can say that the solution x of t is equal to x naught cosine omega t. So this is the solution to this type of problem. X naught cosine omega t plus phi. We can include phi. Some books include a phi, some do not. So depends upon which book you have. In your textbook, they don't have the phi. I have 2 books in front of me here. They don't have the phase phi. Phi is a phase difference, but we can use the phase difference. It doesn't really make any difference. So omega is equal to 1 over the square root of LC. All right, and x naught is equal to initial charge Q naught. So we can replace those quantities by saying that Q of t is equal to Q naught cosine omega t plus phi, and we say omega is equal to square root of, omega is equal to the square root of 1 over LC.
Is that QT?
Q of t. This is Q of t. Q is a variable, so Q of t is given by that quantity. Any questions on that? And then you can, obviously, you can find current by taking the derivative. Okay, so we can find the current. So we find current I of t by differentiating Q of t. All right, any questions? Okay, so we can plot a graph of charge versus time. Let's show you a graph of charge versus time. So this is Q of t versus time. So this is a cosine graph, as you can see. So this is the charge of Q of t versus time, and this will be Q naught, and this is minus Q naught. Okay, so that's just a cosine graph. Let me redraw it. I started the wrong way. Okay, so this is what I want. So that's your cosine graph.